Hey, you guys. Um, so I know that Dr. Bray Ali isn't everyone's cup of tea in terms of a substitute. We did go over some practice problems in his very abstract way, so I'm gonna try and turn them into a more concrete problem. So one of them was a train that can accelerate 20 centimeters per second squared and then decelerate 100 centimeters per second squared. You can go ahead, pause, try and work out. Oh, sorry. And you have to find the minimum time for the train to travel 102 kilometers. So I'm going to make that as x. So go ahead, pause, try and work it out. What I think we ended up doing was we used the graphs. So if you remember, if you have like a velocity versus time graph and you do like a straight line there, if it's slanted, then the slope is going to be, the slope is velocity over time, right? And we know acceleration is velocity over time. So then the slope is acceleration, right? And the same goes for like if you have a x and t graph, distance and time, then the slope is velocity in that case. But given that both accelerations are constant, also, I hope that this looks better than it has been. My boyfriend's letting me use his tablet, so the writing's a bit faster. So what I'm gonna do is we're gonna draw the 20 centimeters per centimeters second squared and the 10 centimeters second squared on the graph, right? Remember that because it's deceleration, that one's gonna be negative and the acceleration is gonna be positive, given that our x direction is the direction of travel. Right, so if you're accelerating into the direction of travel, you're going to have positive. If you're decelerating or slowing down against the direction of travel, then it's going to be negative. He did do some weird ratio. I think it was because he did like slow to accelerate ratio, so that's 100 to 20. Which I think divides down to like 5 to 1. And then from there, he said, okay, assume out of 60 seconds or a minute, then you would have like 50 seconds to 10 seconds, right? So it all adds up to a minute. And then from there, he calculated like the velocity of both sides and then realized that it wasn't, it didn't add up to 1.2 kilometers. So then from there, you just know that you have like, it goes from 0 up to some V max. And then it slows down a lot faster than it sped up. And that's your total time here. No, not acceleration, it's velocity. So then you know that this one over here is a 20 rise per 1 second. And this one over here is 1 second per 100 centimeters. And then this comes from calculus, but the area under a graph is the same as the integral, I believe. So, right, if you just had constant velocity and then you stopped here, Then the area under the graph would be the constant velocity times your time. It would actually be here because the velocity is on the y-axis and the time is on the x. And then your x would be vt, right? So then the question is, what does this time have to be for area under the graph to be 1.2 kilometers? And then that's where he stopped. So I think he mostly just wants us to understand the graphs and I can understand the graphs, and that the space underneath is the integral and the slope is the derivative. So how can I do that conceptually? Let's do xt vt and at, right? If you're going this way, then you're taking what? The derivative, right? So then your x is probably going to be squared. The units would have to cancel out, so it would be like meters over second squared. We're assuming constant acceleration, by the way. So your t squares, you're going to have like an exponential, parabola graph. And then your velocity is going to be like meters over second squared times of t, right? That's linear, so it's going to go up linearly. It doesn't have to be from 0, but from v naught. And then your acceleration is going to be like a straight line. One, I'll just do t to the 0. This would probably be 1 over 2.
That's funny. He's talking about a birdwatcher song.
So then here, the slope is acceleration. Here, the slope at a given point is the instantaneous, or the velocity, average velocity between those points. The same goes for the velocity, but because we drew it as a linear line, the slope's consistent throughout. And then the area under the graph, let's change color, of the x is the nothing for x. Yeah, because you don't take the integral of x. For the velocity, it's x. And then for the acceleration, it's velocity. Okay? Alright. The other one that he did was, sorry, I'm opening up my phone. He throws a small ball vertically up into real air with drag. How long does it take to go up and come down? So this would normally be like a free fall problem, right? But he's asking you with drag, which is something we haven't covered. So drag is a lot like force friction. It acts in the opposite of motion. So then when you're going, bless you, when you're going up on the left hand side, right, then the force drag is going to be downwards because it's acting opposite of motion. And then when you're going down, the drag is going to be forced upwards. And then he did this whole thing about like the ground. Like he flipped the axis so the ground's above you. And then the ball's falling upwards. I think that's just how he's imagining it. It should be the same, the opposite. So ground's below you, the ball's falling. Right, but with force drag, here is going opposite of motion, right? So it's gonna slow you down, right? Because you have gravity, acceleration heading downwards, and then you have drag force going upwards. So then if you were to like go up and go down without drag, you'd probably go higher. Because you don't have that opposing force acting on you and slowing you down. He did do some of his mental math. I did not catch it all, so that's about all we're getting for this problem. And then I did want to do some of the exam 1 key practice. If it will load. And this looks a lot more like what we've been doing. So we have a box on an inclined slope. And then we have the mass is 50 kilograms. And then you have a force of 330 newtons, which is pushing the box up the hill. So that's force push. And then don't forget that we always have normal force and gravity. So you have force push going along the incline, normal force going perpendicular to the incline, and then gravity going down. So we're going to need to find the XY components for that. It does give you the incline angle, which is 25 degrees. I'm going to do a little thought bubble on this side. So you have your incline and you have gravity, which is coming straight down, right? And then you have this angle, which is perpendicular. There are two ways you can find the angle for gravity. We know this one. And we know that this one, the gravity is perpendicular to the ground, which is the same like x-axis that your reference angle is from. So then you can remember that a triangle, all angles equals to 180, right? So then you have your 90 degrees plus your 25 degrees plus your unknown is equal to 180, and then you can solve for it that way, which 90 plus 25. So then your unknown would be 180 minus 115 is your unknown, which equals 65 degrees. So then you have that angle, and from there you can find the x and y components, or you can use that to again find this other angle, which sometimes is easier. So let's go ahead and draw the x and y components. And remember that we're doing x and y components in reference to the angle, to the incline, sorry. So then this one here would be our unknown, right? Because we have this being our incline. Okay. Let's define our axis real quick. I'm doing along the incline as x and perpendicular as y. So then, force gravity is going to be x, which is adjacent. So cosine. So then you're gonna have force gravity over oh wait, no, it would be the hypotenuse there, huh? Just go ahead and label them real fast. Hypotenuse. Oh no, you're fine, because those lines were just to show you that how you get that angle. So then you have your adjacent over here, hypotenuse, which is your force, and then your opposite angle over here. So adjacent cosine, that stays the same. So then you have cosine, which is equal to adjacent over hypotenuse. Put the hypotenuse over, which is your force. So then you have force G, cosine, I'm just going to put question mark, which that turns into mg. And then you do the same thing for y. That one's on the opposite, so you're using sine, which is opposite over hypotenuse, which becomes hypotenuse sine opposite, which that becomes force gravity sine mark just get there. And then from there we can sum up our x and y forces. So be given that we're not, oh yeah, we are doing friction. Oops. The coefficient for friction is 0.33. So we'll start with, first we're going to need to find the normal force to find the friction. So we'll start with the y. So sigma f of y is normal force plus force of gravity on the y, which is negative. So then that's going to become normal force minus your mg cosine. No, sorry, that should be sine. Sine. Mg sine theta. Be given that you're not moving in that area, your total acceleration is 0. So then that's equal to 0. So then your normal force is equal to your y component of gravity. And then from there, you're going to do your, we could probably start with finding the force friction. So, force friction should be normal force times the coefficient of friction. So the little side bubble. Yeah. The force push. We could probably put the negatives to start with. Just keep in mind that you're adding all of the forces, but the ones that are opposite from your axis are negative. So, force push. Plus it would be negative force friction plus negative force gravity on x, sorry. There's an MA. We don't know if acceleration is 0 yet, so we're going to leave it as MA. And then from there you can plug in, I'm going to start with just plugging in symbols. Force push minus normal force, mu, which is your coefficient of friction, minus mg, should be cosine theta, is equal to ma. And then you're going to plug in force N for force friction, normal force. I know there's a way you can combine this sine and cosine. I'm just going to look up the trigonometry rules real quick. Or maybe that's later. Yeah, I think later on you're going to have to combine them. But for right now, you don't have to worry about that. Okay. And then we can just plug it all in to find acceleration. So we could divide everything by m here. Then you plug it in. I'm going to just change color just so that we can see. Go to force push, which is 330 newtons, minus gravity, 9.8 meters over second squared. And then you're going to have, I'm just factoring the gravity out. That's what I did there. Sine 65 degrees plus cosine 65 degrees, which I'm just plugging into my calculator. Oh, divided by m here. Oh, the problem does say mass is equal to 50 kilograms. The reason I knew I was missing something was because we were doing newtons minus meters over second squared. And remember that a newton is equal to kilograms meters over second squared, so you can't like subtract it from just meters over second squared. Divided by 50. Okay. It's negative 6.4. Just making sure I plugged everything in right, because it is negative, so. Okay. It all looks fine. So, just note that it's negative acceleration, so you're actually going down the hill. So, the poor people pushing this box aren't having it. I feel like I'm missing something. Oh, you totally forgot to include mu. Right here. Mu. So then for the sign, you would just multiply mu in there too. 0.33. Sorry, you guys. I usually do the problems in class, but I haven't been doing that for evident reasons. 0.33. And then that gets us the actual answer of negative 0.47. It's still sliding downwards, but not as fast. Alright, and that's all for me today. Kaleo, how do I start the recording?
Did you start it?
Yes, it's blinking right there.
Oh, right here.